Okay, welcome back. Dr. P here, and we're moving on into chapter 16. And in this lecture, we'll look at one of the reactions, actually the main reaction of aromatic compounds, which is electrophilic aromatic substitution. All right, now previously we saw electrophilic addition to alkenes. Where we might have something like cyclohexene reacted with bromine, and we will add the Br2 across the double bond. Notice that this is an addition reaction. Our bromine, Br2, is our electrophile. Now, I also mentioned, in I think it was the first chapter 15 lecture video, that if we try this reaction, with benzene, we get no reaction. So instead, we end up with an electrophilic substitution. Oops, let me see if I can spell correctly today. Electrophilic aromatic substitution. And that is, we have our aromatic compound, which could be benzene, it could be a derivative of benzene, and we'll talk about that in future lecture videos. And we'll use our bromine, but then we'll also have a Lewis acid catalyst. And together, these guys are going to make the electrophile. So I'll just circle that in blue. So we'll say together make electrophile. We'll take a closer look at that in a little bit. Anyway, the product we get is not an addition product, but rather a substitution product. So again, we've got a substitution reaction, not an addition reaction. We call it electrophilic because we have something acting as an electrophile, so our aromatic compound is going to be the nucleophile. So let's take a look at this mechanism. I've got a new piece of paper here. Let's take a look at the mechanism in a little bit of detail. So I'll just abbreviate electrophilic aromatic substitution, EAS. So in general, where E plus is the electrophile, and B is a base, we get the following. Now I'm going to go ahead and draw in the hydrogens, and as I frequently say, drawing in the hydrogens can help you keep track of where your charges are. So we'll have our electrophile, whatever it is, and we'll take a look at, we'll start off with the example of halogenation. We'll take a look at what the halogenation electrophile actually looks like, but I want to go over this general mechanism first. We'll go ahead and get attack on the electrophile by pi electrons there. And that's going to give us now a bunch of different resonance structures here. So we'll go ahead and we'll have our hydrogen, we'll have our electrophile, we'll have hydrogen there, hydrogen, 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 hydrogen. We still have these double bonds, and we're left with a positive charge on that carbon. So not the carbon the electrophile goes to, because that's got 4 things on it, but the other carbon at the other end of that double bond. Now, of course, we have some resonance structures, so I'm going to go ahead and draw in some arrows here. Boom, boom, H, E, H, 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 H. So positive charge on that carbon. And then I could also push electrons down there. And that gives me now, boom, boom, H, H, E, H, H. Positive charge is on that carbon right there. And then the final step here is to remove our extra proton here. So I'll have my base, and then I'll just come in, and now I can get these electrons going down there, and I will get my product, which is my substituted benzene. I've now substituted the electrophile for a hydrogen. So plus BH plus in this case. So this is the basic mechanism, or the core mechanism, the essential mechanism. We have addition of the electrophile. So electrons from the pi electrons grab the electrophile. It makes a resonance stabilized intermediate where our positive charge is delocalized over 3 carbons in the intermediate. And then a base comes along. We don't have to add the base. Well, actually, the base will be typically present as, part of the, after we add the electrophile, the rest of it will act as a base, for example. Anyway, we'll go ahead and remove a proton here, and then those electrons will go to regenerate our aromatic system. Okay, now you want to be familiar with this. You want to be able to do this repeatedly in different iterations with different electrophiles. So let's take a look at one of those. Let's take a look at one of those iterations here. Let's take a look at halogenation. So we'll go ahead and have our benzene here, and then we'll add X2 and use AlCl3 or FeBr3. And then X is going to equal Cl or Br. So typically we'll only do a chlorination or a bromination. I2 is not reactive, or not very reactive. And then F2 is too reactive. That is, it's difficult to control. Now this is our Lewis acid catalyst. We're going to match that to the halogen. So if we have Cl2, we'll use AlCl3 as our Lewis acid catalyst. If we have Br2 that we're trying to do the substitution with, we'll use FeBr3. And we end up now, of course, getting our substitution product, which we've seen before in the bromine example, plus HX. Okay, now what does the actual electrophile look like? Well, for bromination, we have our Br2 complexes with the FeBr3 to make something that looks something like this. Br, Br. So this is our Br2. And then Fe, Br, Br, Br. Put in all my lone pairs. So this ends up with a negative formal charge on the iron and a positive formal charge on that bromine. Now in reality, because bromine is more electronegative than iron, we don't have more electron density on the iron. However, the whole purpose of the FeBr3 is to make the Br2 a better electrophile. Okay, so this very electrophilic. So that bromine specifically is going to be very electrophilic. Why? Well, if we have some pi electrons that can come along, make a new bond to the bromine, these electrons then get kicked off onto the bromine there, and we'll get an FeBr4 FeBr4 minus ion, which we no longer have the positive formal charge on a bromine, and the negative charge is spread out over all the other bromines. Okay, so that's our electrophile. And then the chlorine, for using chlorination, we're going to have a similar electrophile, but we'll have chlorines instead of the bromines, obviously, and we'll have aluminum instead of iron. You could use FeCl3 or you could use AlBr3, but typically these are the reagents that are used. So again, for chlorination, we'll have chlorines instead of bromines, and we'll have aluminum instead of iron. All right, now let's say you have to go ahead and draw this mechanism. What's that going to look like? Well, we'll do the following. All right, so we'll start with our benzene here. And we'll have our Br, Br, Fe. I'm just going to write it as FeBr3 here, but I am going to put my electrons there. Positive formal charge on that bromine, negative formal charge on the iron, and we'll go ahead and get attack on that bromine at the end. And this will now give us, I'm planning for my resonance structures here, this will now give us the following cation intermediate. And then you do need to draw all of your resonance structures. So I'll go ahead and draw those in here. Positive charge is going to move over there. And then we'll have our third resonance structure. Positive charge up there, Br and H. And now our base can come along, and the base actually has the following form. In this case, it's our Br, FeBr3, and this comes along. We've got, again, got our negative formal charge there, and it's actually electrons from that bromine, so it's essentially functioning like a Br minus. And now those electrons go down there like so. And that gives us now our final product. Oops, sorry, I screwed that up there. Let's draw it down here. I mean, it would be the same anyway, but I just want to show you consistently where things are. So I'm pulling off that proton, electrons go there, regenerate that bond. Sorry about that. Plus HBr. All right, so there is our bromination mechanism. So this is our brominated benzene derivative here. And notice the similarities here. So we have in the general mechanism, let's see if I can squeeze all this in here. We just have our electrophile. This is our actual electrophile. So now we've added the bromine here, which is what is the equivalent of the E on our general mechanism. And then this species acts as the base to deprotonate. So here we just had our generic base. All right, so that's bromination. Now, we have some other reactions that we can also do. And I'm not going to go over these mechanisms, other than I'll show the mechanism of formation of the electrophile. Because again, the mechanism is going to be the same, only we've got a different electrophile. So we could have nitration, where we have our benzene, and we're going to react this with HNO3. How do I want to write this out here? Yeah, let's do it this way, sorry. We'll do our benzene. Sorry about that. Let's start over here. Plus HNO3, and we'll use concentrated, we'll abbreviate that CONC, concentrated nitric acid, and we'll also use concentrated sulfuric acid, and that will serve as our Lewis acid. And then we'll end up with our NO2. This is our nitrated species here. Okay. Plus, we should get water as our byproduct here. We don't really care about that. We're interested in the organic compound. Now, how is this electrophile made? Well, the key here is that we have concentrated nitric acid and concentrated sulfuric acid. Although these are both considered strong acids from, Chem 1A and Chem 1B, it turns out that sulfuric acid is actually a stronger acid than nitric acid. And if you use concentrated sulfuric acid and concentrated nitric acid, you can actually protonate nitric acid. I know that seems a little weird. So let's take a look at how that would happen. So we'll go ahead and I'll draw a Lewis structure here for so here's our nitric acid. And then we'll have HO, I'm not going to draw the rest of, I'll just call it SO3H, rest of our sulfuric acid. And so what happens is we get protonation, and now we have NOH, lone pair, positive charge, double bond O, O minus there, positive charge there. And now we can lose water, and that will give us O double bond N double bond O, positive charge, plus H2O. And this guy right here, our NO2 plus ion, is the electrophile. So we would have our electrons from the pi bond here adding to the nitrogen of the NO2 plus to make the or to add the electrophile. And then later we'd have something come along as a base. We could use water as a base, for example. We could use SO3H or SO4H minus as a base if we wanted to. Water would probably be the more likely base. Okay, so that's how we make that electrophile, and then the mechanism is the same as what we've seen. All right. There's another couple reactions actually that I'd like to go over here, and I'm just looking at the time, and I don't want to make this video too long, so let's take a look at sulfonation. And for sulfonation, what we'll have here is we'll use SO3, and then we'll do this in H2SO4, and we will get S double bond O, double bond O, OH. We'll get a sulfonic acid here. So that equals SO3H. Now notice that this is reversible. So if we have dilute H2SO4, so just a little bit of acid, it actually favors the reactants, favors the reverse reaction. And if we have fuming sulfuric acid, what's fuming sulfuric acid? Well, that's SO3, sulfur trioxide gas, and H2SO4, which is concentrated. So essentially you've bubbled SO3 gas into concentrated H2SO4. And of course our electrophile here, or not of course, but our electrophile is actually SO3. So that's going to look like this, and again we'll get attack from the pi electrons on the sulfur here. That'll kick some electrons onto this oxygen and make a negative charge, and then we can just pick up a proton from the H2SO4 to go ahead and protonate that. Alright, so that's sulfonation. Let's see here. Couple more. Let me just check here and see. see, I'll introduce you to the next couple of reactions, and they are the Firedel-Crafts reactions. So we can have what's called a Firedel-Crafts alkylation. And we will go ahead and we will take our benzene, and then we'll add some kind of alkyl halide here, and we'll use our AlCl3. We'll use our Lewis acid catalyst, and then we'll end up sticking CH3 on our benzene ring there. And in this case, our electrophile is going to be as follows: H3C, Cl, Al, Cl, Cl, Cl. So it's kind of like we did with bromination, or chlorination for that matter. And now we can get this bond breaking there, and we get H3C plus AlCl4 minus. So essentially this is our electrophile here. All right. Now, there's a limitation here, and the limitation is that if we try to do this with, let's say, a longer chain, so we could do it with methyl chloride, we could do it with ethyl chloride, but if we tried it with propyl chloride, we find something interesting happens. We end up getting isopropyl benzene instead. What we get here is a rearrangement. And that's because when we make the electrophile, it's going to rearrange. So we would make CH3, CH, positive charge. Now we could go ahead and get a hydride shift. Remember those from 12A. And that will give us now H3C, CH, positive charge there. We get our more stable secondary carbocation. So this is one limitation of the Firedel-Crafts alkylation. I'll talk a little bit more about a couple of other limitations with the Firedel-Crafts alkylation, but we'll do that, I think, in the next lecture. The last reaction that I want to get to in this lecture is another version of the Firedel-Crafts reaction, and that is the Firedel-Crafts acylation. So let's take a look at that. I'm going to keep that guy up there for right now, Firedel-Crafts alkylation, and we'll do our Firedel-Crafts acylation. Here we will be adding the following kind of group. So we'll have R, C, double bond O, Cl. This is what's called an acid chloride, or an acyl chloride. And again, we'll use AlCl3 as our Lewis acid catalyst. And we will end up getting now our acylated benzene plus HCl. And again, we'll make an electrophile which looks like this. We would have R, C, double bond O, C, A, L, sorry, Cl, Al, Cl3. I'm just going to write that. I'm not going to draw out all the chlorines. And then we would have a positive formal charge there, negative formal charge there. We'll actually get the CCl bond breaking to make a RC double bond O plus and RC triple bond O plus. You get that following resonance structure. And this is an acylium ion. And this is the actual electrophile. So instead of making a carbocation, oops, I wanted to try to keep everything on here. All right, so instead of making a carbocation like we did with the Firedel-Crafts alkylation, we make this acylium ion. Now we've actually controlled where things are going. So this guy will not rearrange, not prone to rearrangements. All right, so this guy won't rearrange. Now, you may be asking, well, I wanted to put a propyl group on my benzene to start with. So, how do I do that? Well, that's where you have to do an additional step. So, let's say we use our propanyl chloride here. And that will give us now the following product here. And then we can reduce this carbon to eliminate that oxygen. And we'll do that with zinc and mercury. That's a zinc-mercury amalgam. So those are the two metals like mixed together. And HCl aqueous. This is called a Clemmensen reaction. And now that gives us our propyl benzene. So this gets around the limitation of the Firedel-Crafts alkylation. There's some other limitations of both the Firedel-Crafts alkylation and Firedel-Crafts acylation, but I think I will save that for a future lecture video. All right, so go ahead and review the electrophilic aromatic substitution mechanism. Practice it, the general mechanism and the specific mechanism. So again, I drew out the one for bromination, but you can give it a try for nitration and sulfonation and even the Firedel-Crafts reactions. All right. Well, next time I'll talk about what happens if we start out with something other than benzene. What if we have methylbenzene? Or what if we have, I don't know, phenol, so hydroxybenzene? We'll take a look at those. All righty. Until next time, stay safe out there. Bye now.